Good evening and welcome to the Arundel Camera Club virtual live stream for Thursday, March 24th, 2022. My name is John Milliker and I'm the club president for the 2021-2022 season. The Arundel Camera Club was founded in 1957 and exists to promote the arts, science, and education in all aspects and fields of photography. For more information about us, please visit www.arundelcameraclub.org. Thank you for joining us on our virtual live stream. With the help of our members and officers, we've made the tough decision to stay virtual until the end of our club year to start back up hybrid in September. Also, you have received either a poll question in Facebook or an email. We believe we'd like to try to have our May banquet in person, and we need your help to help decide if we're going to have enough people that feel comfortable coming out. So if you haven't already filled out the poll on Facebook or maybe replied to the email that I sent out, please do so. And for tonight's amazing program, here's our upcoming schedule. This Saturday on March 26th is our field trip to see the cherry blossoms in Washington, D.C. And then on Thursday, March 31st is our friend Quinn Jacobson with the collodial albumin negatives and gum over palladium prints. As you may remember, Quinn joined us last year, or maybe it was 2 years ago, and he works in a lot of the chemical and the alternative processes. And his thought process on that is going to be something that's going to be very interesting to everybody. So make sure you join in on that. And then on April 7th, we're going to have a photo review of our March entries for our March contest that we just had. And on April 14th, we have a TBD there because it was a night that we had an in-person only speaker. And I know that our programs team is working on filling this spot with another exciting program. We're extremely fortunate to have Joseph DePasquale with us tonight. Let me make sure I get Joseph up on the screen. Hi, Joseph.
Hello.
Joseph is the Senior Science Visuals Developer in the Office of Public Outreach at the Space Telescope Science Institute. Prior to joining STSCI in March of 2017, Joe was the science imager for NASA's Chandra X-ray observation at the Smithsonian Astrophysical Observatory, where he worked for 16 years following his undergraduate training in astronomy and astrophysics at Villanova University. Joe has an extensive background in astronomy as well as art and photography, giving him a unique skill set well suited to the task of bringing raw observatory data to life in press-quality imagery. At nearly 32 years in orbit, Joseph shares there's an entire generation of astronomers and space enthusiasts alike and have always known the Hubble Space Telescope's unique perspective on the cosmos. Joseph says the story of Hubble is just as fascinating as the beautiful imagery and groundbreaking science that it continues to provide. Joseph, thank you so much for being with us. Oh, I got a little bit more. After a brief overview of Hubble's early days and servicing missions, we'll take a look at some of the observatory's recent iconic imagery and discuss how it was made. We'll also take some time to review the current status of the James Webb Space Telescope, which was successfully launched on Christmas Day in 2021 and has continued to see outrageous success in every part of its commissioning phase, working towards the beginning of science operations this summer. Now I'll pass it over to you, Joseph. Welcome.
Thanks for that introduction, John. I'm going to share my screen now.
Okay, we're extremely excited to have you here, everybody. Welcome everybody in the live chat. If anybody has any questions, please go ahead and put them in the live chat. And Joseph has asked me to interrupt him. That way we keep everything kind of fresh. And whenever you're ready, Joseph, let's go ahead.
Okay, sounds good. Okay, is everyone able to see my screen now?
Yes, sir.
Okay. Thanks again, John, for that introduction. I'm sorry I wrote so much text and you ended up reading all of it. But so I've been with Hubble for about 5 years now, and it's been it was always a dream to be able to work for Hubble, and the fact that I'm doing it now is it's amazing. When I first started, I was actually working with Zolt LeVay, who was the science imager for Hubble from the very beginning. And so a lot of the work that Zolt was responsible for was actually in some ways inspired me to get into astronomy to begin with. So to be able to share an office with Zolt and learn from him before he retired, that was such a unique experience. And I'm really glad I was able to do that. But let's jump in. We're gonna talk a little bit about Hubble, as John said. It's coming up on 32 years in orbit. So as I wrote in my introduction, there is an entire generation of people, of the science interested public, the general public, astronomers. There's a whole entire generation of people who only know the universe as it's seen by Hubble, and it's quite a view that Hubble provides for us. Hubble is probably one of the most successful scientific endeavors in human history. It's had an undeniable impact on science of our understanding of the universe, and it really has captured the public's imagination. There's a really interesting sort of nexus of the launch of Hubble in 1990 coinciding with sort of the growth of the internet. And Hubble was one of the first NASA missions to really take advantage of the internet as a means of transmitting information and imagery and science press releases from Hubble to the general public. And so seeing those two things sort of grow together really put Hubble in a unique place to sort of capture the public's imagination. In terms of like metrics for how Hubble has impacted science, there's about 950 papers per year published with Hubble data. Over 800,000 citations per year, 600 plus PhD theses, which comes out to like one per week, 2 papers per day. 1 in 6 astronomy papers use Hubble data. And so Hubble is just this amazing powerhouse of astronomy, and it continues to be so, 32 years and going. And we're in a really unique spot now to be able to take advantage of Hubble and the Webb Space Telescope coinciding in orbit together for some amount of time. We know that Hubble has a limited lifetime, but it's still going strong. So we plan to do coordinated observations between the two observatories. For the photography buffs, Hubble has a focal length of 57,600 millimeters at an f/24 aperture. I always like to throw that little fact in there. Now, of course, I'm talking in glowing terms about how Hubble has impacted astronomy and the general public, but it wasn't always this great for Hubble. If you aren't aware or you haven't followed the story of Hubble from the beginning, it actually had some serious problems when it first launched. There was a mistake in the grinding of the mirror, and I'll get into that in a couple of slides, that caused Hubble to not be able to focus as well as it should have when it was first launched. And that was in 1990, and it took about 3 years until there was a servicing mission to be able to fix that problem. And so during that 3-year period where Hubble was not able to really focus well, it became sort of the butt of jokes. And in fact, we got NASA's $1.5 billion blunder. NASA loses, or Hubble telescope loses a large part of its optical ability. Again, this was caused by a very slight mistake in the grinding of the mirror that caused a spherical aberration. It was due to miscalibrated equipment at Perkin-Elmer Corporation, who were actually built the mirror. And that aberration was 1/50th the thickness of a human hair. And so, you hear this term, what is a spherical aberration? Well, in a perfect optical system, the mirror is able to focus to a point where this F is in our little graphic here. That is the focal length of that mirror and that telescope. And when you have a spherical aberration, there's a mismatch between the focal point and the shape of the mirror. And so you're not able to find the perfect point where all of the reflecting lines come together to create a full focus. And so that's what we mean when we're talking about a spherical aberration. Now, I make it sound really bad, but Hubble, although it had this spherical aberration, still produced images that were very much better than what could be produced by other telescopes at that time, which were, of course, limited to ground-based astronomy. And so if you compare this image here of a star, when Hubble still had its focusing problem, compared to a ground-based observation of that same star, there's clearly a big improvement there. But that didn't stop the general public from sort of lampooning Hubble in its first 3 years. It was, the butt of jokes in the news. Here's another example. It actually became a definition to do a Hubble was to make an outrageously stupid mistake at an exorbitant cost. That was really bad times for NASA during this time. But thankfully, we had the astronauts who were willing to risk their lives and go up and service Hubble. And it was designed to be serviced, but it was never quite designed for the kind of service that was required to do the repair to the mirror focus. And I would like to point out that before this mission, so SM-1, Servicing Mission 1 in December of 1993, the telescope had been up there for 3 years. It was taking real science data. And software engineers at the Space Telescope Science Institute developed software to enhance the blurry images and calibrate out some of this spherical aberration through software. which actually led to downstream development of useful image processing tools. Now, this servicing mission, this is when the astronauts installed WIFPIC-2 to replace WIFPIC-1, and CoStar, which was actually, that's sort of the contact lens that was put in place to fix the spherical aberration. Instead of replacing the entire mirror, which would have been pretty much impossible, we put something in front of the mirror to counteract the effects of the aberration, and that was called CoStar, which is Corrective Optics Space Telescope Axial Replacement. It's a mouthful. Now, after CoStar was installed, there was a dramatic improvement in the focusing ability of the telescope, and all of a sudden, everything came into focus. The universe was, Hubble's oyster to observe. There were press conferences to show off the new results from Hubble. This is Senator Barbara Mikulski displaying Hubble's new image of the core of the galaxy M100. A few years ago, we celebrated this milestone with another press release, which compared that core of M100 from WIFPIC-1 in 1993 to the installation of WIFPIC-2 in 1994 to then the installation of WIFC-3, which was the last servicing mission to Hubble in 2009. And this we put this out for the 25th anniversary of servicing mission 1. And then this is a wider field view of the same galaxy M100. And you can clearly see that improvement in the focusing ability of the telescope, but also that original data set wasn't so bad. And now public opinion starts to turn, and Hubble becomes a little more popular, and NASA's starting to recoup some of the egg on their face. Hubble is now able to do the science that it was meant to do. It took a few years, and it took a lot of planning and work, but it was a success, and it has been ever since. And it just so happens that soon after the servicing mission in December of '93, we discovered that there was a comet, Shoemaker-Levy 9, was on its way with an impact course to Jupiter, and Hubble was perfectly poised to be able to observe that with its fresh new optics. And of course, if you remember this, the results were just absolutely stunning. Here is a press conference where that astronomer in the left there, that's Heidi Hammel. She interrupted the press conference to show off the new results because they had just come down from the telescope, and the pictures were just incredible. Be able to see this impact scar of a comet on another planet, something had never been seen before. And again, Hubble, just the perfect timing of having that fixed to the mirror just in time to see this. It was really quite serendipitous. And again, I will remind you that the main reason for Hubble's power, again, is because it's in space. So it's orbiting above the Earth's atmosphere, which of course has distorting effects on what we can see from the ground. And its longevity in space is due in most large part to the astronauts who risked their lives to go and upgrade Hubble and repair problems with Hubble on 5 different occasions. Of course, being in space and doing this kind of work is very difficult, but Hubble was made to be modular, and the astronauts were able to take advantage of that and install the necessary equipment to keep Hubble running. One of the most I guess the limiting factor of Hubble right now is the gyros, and the gyros are what keep Hubble able to point. We have there's 3 of them, spinning gyros, actually more than 3, but you need 3 to get the 3 axes of movement to be able to point Hubble accurately wherever you want in the sky. And they don't last forever, but the current crop of gyros are doing really well. I'm knocking on wood. We want to see those continuing to perform well. Now, for the next few slides, I'd actually like to go in depth, dive into the telescope itself so that I give you some context in terms of what I'll be talking about a little later as we talk about the images and how they're made. And so here's a very basic look at sort of the interior of Hubble. You can see there's the main optical pathway there with the secondary mirror sort of hanging in the middle by the support struts, and then the primary mirror at the back. And of course, the secondary mirror bounces light off the primary down into the science instrument section, which we can see in a little more detail in this slide. So we've got the secondary mirror taking that light down into the science instruments. And, all of the text on here is kind of, we don't really need to concern ourselves with that right now. I'm just trying to give you an idea of the sort of interior structure of the telescope. there's the pathway of light goes down that tube, bounce off the main mirror, the secondary mirror, into the science instrument module. And then, just as an example, here is one of those main science instruments, the Wide Field Camera 3, WIF C3 as we call it. And down at the bottom there, in the bottom right, you can see pickoff mirror. And I'm going to back up and look at this slide again. So this instrument module sits at the back end there where it's blue and it says instruments. Just next to that, WIF C3, that's the instrument module we're talking about. So that pickoff mirror sits right in the middle of that the light path as light's coming through to the instruments in the rear of the telescope. And so that pickoff mirror literally just takes some of that light that's coming in and sends it into the instrument module for WIF C3. And it's got a bunch of mirrors in there, an optical bench that takes that light and disperses it through filters and gratings and ultimately down to the detectors to make imagery and spectra. And one of the most interesting things I think about Hubble is it really does literally have like physical mechanisms for the filter wheels to be able to take images in different kinds of light. So the main WIF C3 detector is 2K by 4K CCD. So you and there's two of those, so you end up getting a 4K by 4K. It has 4/100th of an arc second per pixel resolution and a field of view of 162 by 162 arc seconds. And again, all this information is just kind of throwing that out there if it is relevant to you. It actually has 48 total filter slots, which encompass wideband, medium band, and narrow band filters. And Hubble is actually sensitive to light all the way from ultraviolet into near infrared. And speaking of infrared, I'm going to shift gears here for a second and talk a little bit about the Webb telescope. As John mentioned, Webb was successfully launched on Christmas Day last year, 2021, and it's currently in its commissioning phase. So it's made its way to its final destination at the Lagrange point L1, and it's currently in that orbit. It's literally 1 million miles away from Earth. And everything that it's done since launch has just gone off amazingly well, like better than anyone could have imagined. The first few weeks after launch were probably the most mission critical. There were a lot of potential like single point failures during this time. Because if you may remember, if you follow this, that the Webb telescope was too large to launch in its final configuration. So it had to be folded up to fit inside the Ariane 5 rocket that launched it. And the unfolding sequence was just some nail-biting experience that the engineers at Space Telescope were just, watching with bated breath to make sure that every step of this unfolding procedure went off without a hitch. And it did. And it was incredible to watch it happen in real time. Everything's looking great. Everything is operating really well. We've actually released an image last week. So as I was going through this, Webb is literally a feat of engineering, and it's just incredible to see it performing as well as it is now, knowing what's to come. The data that we're getting right now is just commissioning data. It's engineering. It's calibration. We're just trying to understand the instruments in their environment in space that they've never been in before. We've calibrated as much as we can on the ground, but you never really know what you're going to encounter until you're up there. But so far, the mirror alignment went off amazingly well. Each one of those 18 hexagonal mirrors has its own actuators and can be, maneuvered ever so slightly to change the focus of the telescope. So we won't have the same problem we had with Hubble with Webb, because we can actually change it from the ground, which is great. And when we did our first observations to check the alignment of the mirrors, the mirrors were aligned before it launched, and then you go through the rigors of launch. The rocket launch, there's a lot of forces. There's a lot of things happening when the telescope is going up in a rocket. So nobody really knew how well the calibration was going to hold once it finally got up into orbit and unfolded and we started testing it. But it did amazingly well. We took a huge field of view and observed a single bright star, knowing that each mirror would sort of create its own version of an image of that star on the main detector for Webb. And we had this huge field of view, and it turned out that the mirrors weren't exactly aligned perfectly, but we were able to find all 18 images of this single star sort of clustered around where we expected they would be. And so that was really just, again, a feat of engineering to be able to see that happen. Now, Webb is an infrared telescope, of course, and I did say earlier that Hubble can see some infrared. So Hubble goes into near infrared. Webb picks up right where Hubble left off, and then extends into mid infrared, um, from near infrared all the way into mid infrared. And it has a huge filter set. It sees at higher resolution in near infrared than Hubble does, and then its resolution drops off a little bit as you go out further in infrared light, and that's just due to the nature of the wavelengths that we're working with. And then, of course, on this electromagnetic spectrum plot that we're looking at, the Spitzer Space Telescope, which is no longer active, there's some overlap between Spitzer and Webb as well. And in fact, I would argue that Webb is more of a successor to Spitzer than it is to Hubble, due to the fact that they're both infrared telescopes. And the improvement that we see so far, we have one star that we've looked at that Spitzer has also looked at, and the improvement between Webb and Spitzer is just really, really dramatic. And that's due in large part to the mirror. Webb's mirror is much, much larger than Spitzer's mirror, and even Hubble's mirror. And if you're going to be looking at infrared light, you really need a large collecting area to be able to have the same sensitivity that like Hubble has in optical light. And as I said, we've been taking data, commissioning data over the last few weeks. This is actually a real image from the NIRCam instrument on Webb. NIRCam is the near infrared camera, and it has a specially designed lens on it called a pupil imaging lens that is designed to, instead of taking an image of the sky, it's defocused to the point where it's actually able to see Webb's mirrors. And so what we're looking at here is an actual image of Webb's mirrors as taken by NIRCam, and they're all sort of flatly illuminated because they're in perfect focus. All of the brightness that we're seeing there is the light of the star that I'll show you in the next slide, focusing its light down into NIRCam, and the pupil imaging lens is looking at the mirrors instead of the star. And so we're seeing each individual hexagon from the 18 mirrors on Webb, and we're also seeing the support struts that hold up the secondary mirror. And this is an important point because the star that we're going to see now, this has a very unique look to it, especially compared to Hubble imagery. This is a single pointing of 2,000 seconds at this bright star that was used for aligning the mirrors. And we see 6 diffraction spikes, along with one that goes across the middle of the star. And up until like a week ago, I had assumed that the diffraction spikes on Webb were caused by the secondary mirror support struts. But it actually turns out that it's caused by the shape of the mirrors themselves. The hexagonal mirrors impart this 6-sided diffraction spike on bright stars as observed by Webb. And then that line that goes across the middle, that's actually caused by the support struts for the secondary mirror. And if you don't believe me, these are simulations that were done before Webb was launched to show what the diffraction pattern could look like on Webb. And so if your aperture is a circle, then you get, a pinpoint of light with diffraction rings around it. If your aperture is a hexagon, you get a 6-sided point. And then if you have tiled hexagons and tiled hexagons with gaps, and then Webb, you can see how it changes from, each one of those. Of course, that bright star didn't quite show the pattern that you see in the core of this bright star here. I can assure you that it's there. It's just kind of blown out because the core of that star is so bright. So we're not really seeing those interesting shaped patterns in the core, simply because of the stretch of that image. But you can see that the introduction of Webb's support struts for the secondary mirror lines up perfectly, puts that line right across the middle. And then just for comparison, this is the Hubble view of what a point of light looks like. Hubble, of course, has struts that support its secondary mirror, and those struts impart its iconic, diffraction pattern of four lines coming through the bright stars.
Joseph, that's really interesting because the astrophotographers of the group, we've used what's called a Bahtinov filter. And I'm not sure if you're familiar with them, but what that does is you put a filter in front of your lenses, and it has these lines going up and down and kind of at an angle. And
right.
If you defocus your star, you can actually see those lines shift depending on how in focus or out of focus you are. It reminds me very much of that.
Yeah, no, I've heard of that before, and I've seen that in different images. So that gives you a diffraction spike in, like, if you were taking images with like not like a telescope, but with a camera, right?
Right. Mm-hmm.
Yeah. Yeah, that's really cool. Okay, so I'm gonna now jump into a little bit of what I do and why we do it. It's not just me, of course, who works at Space Telescope. I have a really talented colleague, Lisa Pagan, who we work together in Hubble imagery and soon Webb as well. And our main goals for the work that we do, one of the strategic goals of the Space Telescope Science Institute is to make astronomical information available to all, available and accessible to all. And I think the press releases from Hubble and the news from Hubble really goes a long way towards keeping people aware of what's happening in astronomy in general, but then also, what's the latest from Hubble and soon Webb. What are we learning from these instruments that we've spent so much time and money building and putting up? And what are we gaining from that? And how is it changing our understanding of the universe? So, my job is to take that raw data from the telescope and turn it into the beautiful imagery that we see to help illustrate these science results. When we have groundbreaking results, imagery always helps to capture people's attention, bring them into the story, and learn more about the science. At least, hopefully, that's the goal. So visualizing the data, engaging and educating our audience, taking that data and trying to maximize its information content. And then, the really key point here is balancing aesthetics and science. Because I know Webb and Hubble, they're both designed as, scientific instruments first and foremost. They're not up there to take pretty pictures. It just so happens that what they can produce for us, in addition to being, amazing science data that helps us understand the universe in new ways, it also produces beautiful imagery. And our job is to take that imagery and, make it look as good as it can possibly look, of course, without changing anything in it. The respect for the data is a key component of the work that we do. We're not introducing things that weren't already there when we process these images, and we're not, we're not altering the images. We're just taking what's there and pulling it together in a way that makes it as beautiful as possible to capture people's attention. And I think of it, and a lot of times I think of it in terms of photography, and we'll get into that in a little bit. But for now, I want to take a little tour of some imagery of old and new from Hubble. Of course, starting with the solar system, our nearest neighbors, Mars, Jupiter, and Saturn. And this Saturn image is actually an animation, which Hubble is not a video camera, and it's not even a color camera, of course. The detectors on Hubble see in black and white. And that filter wheel that I was talking about earlier, that's how we get colors out of Hubble. We take images in different filters and then apply color to those filters, sometimes according to exactly what color they are. And that's how we are able to produce color images. And so to be able to produce an animation like this one of Saturn that shows its moons moving across in somewhat real time, that actually takes a lot of processing and a lot of work to get consistent color, for each image, which is itself a combination of many images. So that's the kind of work we do. Here we've got, of course, the famous Pillars of Creation image. Hubble has provided a gallery of stunning images like these. These are just a few that I've had the privilege to work on, and it really is a privilege. Here we have the Horsehead Nebula, and this was actually taken in infrared. So Hubble's near-infrared capabilities allowed us to see the Horsehead Nebula in a totally new way. We always think of the Horsehead as being this dark cloud in front of a bright background. But in infrared, of course, the background goes away, and we can see the background stars and even galaxies. And the nebula itself glows in infrared.
Joseph, are these what we believe are the correct colors?
Well, so that's an interesting question. When you're getting into infrared, you're moving into wavelengths that our eyes aren't sensitive to. And the colors that are applied here are applied in a way that is chromatically ordered, so that the longest wavelengths of light are colored red. And then as you move into shorter wavelengths, you move towards green and blue. So, it's correct color in the fact that it's chromatically ordered, but it's not something that our eyes could detect. And so to say it's correct color, it gets a little confusing. And then it gets even more confusing when in a few slides, I talk about narrowband filters and, how those colors work.
Okay.
But the beauty of this, what I really see here is, in addition to the deep science results that we get from Hubble, it provides this stream of dramatic, colorful images, and really a lot of these images look like landscapes. And again, that comes back to, at a certain point in the processing of the data, I sort of shift gears in my brain from like a quantitative analysis approach of getting the data into its best form to produce an image, towards then sort of a qualitative photography approach, thinking in terms of like color and tonality and composition. And so here's another example of that. This is the Lagoon Nebula. This was one of our anniversary images. Every year we put together an anniversary image to celebrate the launch of Hubble. That's in April 20th, I believe, is the actual date. And this was the 28th anniversary image from a few years ago. This was one of the first ones that I was able to work on after starting at the Space Telescope. And this was one of those times where I was working on the image, the privilege of being the first person to see this image come together on my screen. That's kind of what keeps me going in this job. It's just so incredible to know that this is going to be another iconic image that people are going to associate with Hubble, and it's going to shape people's perception of the universe. And I had a hand in making that. That's just such a wonderful experience and feeling. Here's the Bubble Nebula. This was an interesting one. This is another anniversary image from the 30th anniversary of Hubble's launch. So 2 years ago, this is NGC 2020, which was partly chosen due to its name because we released it in 2020. This is a really interesting object that we've got this Wolf-Rayet star down on the bottom left that created this blue nebula that stands in very stark contrast to the star-forming region just above and to the right of it. And in that star-forming region, you have a cluster of bright young stars sort of at the top there in the middle that are, carving out these enormous cavities in this gas cloud of hydrogen gas and creating this, landscape of we actually referred to it as the cosmic reef because it kind of lends itself to sea imagery.
Joseph, I have a question for you.
Yeah.
At some point, can you discuss the software you use to pull these images down? And I'm going to add to that. If you could also talk about the software you use and what are the original images? I know you have so many different versions of that image with different filters. How do they come down as well? Like what file format are we talking?
Right. So the data that comes down from Hubble is in a format called FITS, which is Flexible Image Transport System. And it's actually a very old standard that was defined for astronomy years ago. It basically, there's a header file, or the image file contains a very large header that has a bunch of metadata about the image in it. It tells you coordinate information, where this object is on the sky, which telescope was used to take the data, what filters are in this image. All of that is contained in this header. And then, of course, the image data. And the image data are just black and white. There's no color information in a single image from Hubble. So yeah, FITS files. That's the file format that we use. And then in terms of the software I use, I'll go into that a little bit in a few slides. But just to name off a few, PixInsight is where I kind of start. I use that for my image stretch, and then sometimes I'll do my color combination and some of the cleanup in PixInsight. But I transition from PixInsight into Photoshop to do some more of the compositional work, the more like heavy lifting for the cleanup. There's just usually cosmic rays are a big problem. And cosmic rays are just these high energy particles that are, they surround the entire universe, mostly filtered out by the Earth's atmosphere. But Hubble, of course, is above the Earth's atmosphere. And so it's bombarded by cosmic rays all the time. And these particles are high energy enough to penetrate the hull of Hubble, and they can go all the way down right into the science instruments and deposit a charge into the detector. But it's just so happens that these cosmic rays are, they're easily identifiable. And so we can mostly calibrate them out before we even get to the point of creating a color image. But there's always a few that get through, or, if you took a single image and you didn't take multiple images that you then merge together in a mosaic, you might have a lot of cosmic rays. And so there's a lot of cleanup that can be done in Photoshop for that. And just to stress the point that we don't, introduce things that weren't already there, again, the cosmic rays are usually pretty easy to identify. And if they're going to be replaced with anything, it's just going to be the average background level. We're not introducing new stars when we process the images.
There's still photojournalistic integrity up in space.
Exactly.
That's good.
The image that's been up on the screen now, this is AG Carina. This is a very bright star that has thrown a nebula off of itself and is ionizing the gas around it, creating this amazing structure that has this sort of dual red and blue glow to it. And that, again, is due to the filters that we use for this observation that are tuned to look for the light, in hydrogen gas and then oxygen gas. So the oxygen shows up blue here and the hydrogen is in red. Moving further out from the Milky Way, now we're looking at another galaxy. This is the Sombrero Galaxy. And I always love the dimensionality of this image because, the Sombrero is almost edge-on galaxy, and it has this enormous dust lane that runs right through the middle of it. And this Hubble image really captures that, as I said, the dimensionality of this dust lane that runs, goes all the way around the galaxy, but because it's edge on, we see, the leading edge that's towards us is very dark, and it makes this striking band across the center. And then we can also see as it traverses all the way around the other side of the galaxy. Here's a more recent press release. This is one I had the privilege of working on. This was the backup for last year's anniversary image of AG Carina. This is ARP 143. So the ARP catalog is interacting galaxies mostly. So these two galaxies are sort of in a cosmic dance. One is interacting with the other. There's this really interesting stream of stars that are coming off of that very distorted spiral galaxy as it's interacting with that neighboring elliptical galaxy. And then looking even further out, Hubble has the ability to see these amazing galaxy clusters. These are some of the most massive structures in the universe. This is Abell 370. And in this image, what we're seeing is the sort of big blobs of orange light. That is a foreground galaxy cluster. So a huge gathering of galaxies that are so massive when they're all taken together that they actually bend time and space. And that bend creates a lens in space that allows the light behind this galaxy cluster to be focused towards us. So the arcs that we're seeing in this image, the lines that run radially around, those are actually background galaxies that are very, very distant and may not even be observable by Hubble. But because we have this huge lens in front of us, between us and that background galaxy, that lens actually distorts that light that's coming through and bends it towards us again and allows us to see things that are much further away. And I think one of the most interesting aspects of this image in particular is the galaxy on the lower left, kind of around 7 o'clock. There's a spiral galaxy in there that is really amazingly distorted by the galaxy cluster. You can see how it's sort of smeared out and it follows the arcs and contours of the galaxies around it. And that's just a really amazing example of gravitational lensing. And then looking out as far as we possibly can, of course, this is the Hubble Ultra Deep Field. And nearly every point of light in this image, with the exception of a few stars, is a galaxy. So, and this is an extremely small portion of the sky that Hubble just stared at for over 600 hours of exposure time across a decade of observations. And this image combines light from 13 filters, from ultraviolet all the way to near infrared. So pretty much everything Hubble can do was thrown into this one spot in the sky. And we see this just amazing, rich tapestry of galaxies and galaxies of all kinds across space and time. We can see some of the very first galaxies that formed after the Big Bang, all the way up to more recent galaxies that are more fully formed and with structure. And this image was actually the subject of a film that we worked on recently with the composer Eric Whitaker. If you are interested, you can check out deepfieldfilm.com. Eric was so inspired by this image that he wrote a piece of music for it. And he was really interested in working with Space Telescope to develop a unique sort of bespoke set of visuals to go with his music. And so Deep Field Film is where you can find that. Now for, I think what everyone's been waiting for is getting into a little bit of the details about how we do this, how we put these images together. So what I've got here is a sort of very basic example of breaking things down as you know, sort of the way I think about it as we're processing images. There's 3 or 4 levels of processing. And the beginning stages are sort of what I consider the pre-processing, and that is taking the raw data from the telescope and running it through calibration software to calibrate out any of the instrumental artifacts that are there. So the top row of images there, each one of those is an individual exposure of this nebula in different filters. And you can see that there's like very varying background levels in each quadrant of that detector. So all of that has to be calibrated out, and that's what we see in the next level down. And then you take each one of those individual exposures and combine them together to make a mosaic exposure. And the reason you'd want to do that, if you ever do any kind of night sky photography, you take one exposure, you might get some interesting structure in your image, but you'll also have a lot of noise. And you can reduce the noise by taking more data and then combining it together and sort of averaging out the background levels. And so we do a lot of that with Hubble to get cleaner data. And especially for an image that we know is going to be, like a public outreach kind of image, those we'll put the time in to take longer exposures and get like really clean data to make a very clean and crisp image. And so once we've gone through those pre-processing steps, we get to the point where we have a single image in a specific filter. In this case, these filters would be red, green, and blue. And so those filters, they correspond to those colors. And this is the point where I feel it becomes more of a qualitative exercise. And I shift from working in like Python and PixInsight then into Photoshop. And I'm doing more of like a photographic approach towards composing the final image, where I'm considering aspects of photography and visual principles like tonality, color, and composition. Now, one of the very first steps that has to happen when we're working on the imagery is scaling the data. Hubble is extremely sensitive to light, way more sensitive than our eyes are. And so when it takes an image, if you were to open that image in some kind of image viewing program that's just a raw data, that would look mostly black. And that's because if you were to take all of the pixels in the image and sort of lay them out in a plot, which we call a histogram, most of the information is contained in the lower levels. And then the bright stars and the cores of galaxies, that's where we see, if you were to open this image in an image viewing program, you'd see like dots of light, kind of like what we see here. This is called a linear scale of the image. And it doesn't have any kind of bias to it in terms of seeing like low intensity structure. It just shows us low to high in a linear fashion what we see in the image. In order to bring out more detail, we could scale the image and sort of move that brightness level to the left, and you would increase the brightness of the image. The only problem with that is then you blow out all of the bright objects that are in the image. So if you take a linear approach and you move it to brighten the image, now the stars are bright blobs of light. The cores of the galaxies are completely blown out. All this information is being lost. And we call that clipping. So this saturation is a problem, and we don't want to see that in a Hubble image. And so we do something called a nonlinear stretch to the data. And a nonlinear stretch basically creates, instead of a diagonal line across this histogram, you would introduce some kind of curve to it that would allow you to emphasize low brightness features, but preserve the data that are bright. And so in this example here, we can see that the cores of these galaxies are now recovered. Using this nonlinear transform reveals details across the full dynamic range of the image. One of the tools that we use, I don't use this as much anymore, but there's a program called Fits Liberator. It used to be a Photoshop plugin. It was there was Fits Liberator 3, and then just last year, ESA, I was working on this team with ESA, we released Fits Liberator 4. So this is an old image. I should probably update this, but Fits Liberator basically allows you to open a Fits file, which again is the file format that data from Hubble comes down in. It allows you to open that file, do this kind of image scaling that I was talking about. And so you can see here at the bottom underneath, that's this histogram that I was talking about, where you take all those pixel values and you can see them laid out in a plot. And you can see here that a lot of the data is concentrated in the sort of low level brightness of the data. But in order to be able to see all those details, you need to squish the dynamic range into something that's more visible. And Fits Liberator allows you to do that and then write out like a TIFF file that you can then use in Photoshop or whatever image processing software you like to use. Here's an example of using PixInsight to do what's called a screen transfer function. I really like PixInsight because you can work with Fits data. You can do your image scaling with the screen transfer function, but it doesn't actually change the pixel values until you officially apply the transfer function to the data. So it allows you to see what's in the image without actually changing anything, which is, I feel like that's a more powerful way of working with the data, preserving all the information that's there for as long as possible before you scale it. Makes for, I feel like a more robust image processing process. Now, the next step after scaling the data is to assign colors to the data and pull everything together. Again, of course, Hubble sees in black and white, so we have to make this decision for color on our own as image processors. Now, in some cases, it's really obvious how the color should be assigned. So in this case, I'm talking about, quote, natural color. So this is roughly aligned to what our eyes are sensitive to. And the filter names are actually on this image. So F814W is just a filter on Hubble that looks at red light. So it allows red light to come through to the detector, and then anything else is just discarded, doesn't come through. Same thing with the green F555W and the blue F435W. Those filters are designed to allow red, green, and blue light through, so we can assign those colors as they are, and then create a full color image. And again, this would be done probably in Photoshop. But of course, here, this is the sort of raw color image that we get from those individual filters. So we need to do a little more work with this. This needs to be color calibrated and adjusted to really bring out the details in the image to get something like this. And this would just be, adjusting background levels, maybe adding some saturation to the color. We might tweak the colors a little bit here or there. Again, transitioning from analytical to qualitative analysis of the data that's there. Now, where this gets a little trickier is when we're talking about narrowband filters, which, in contrast to the wideband filters we were just looking at that allow like a broad range of red, green, or blue light, narrowband filters are designed to look at a very, very specific small window of the electromagnetic spectrum. And so in this case here, the famous Pillars of Creation image was actually composed of three different filters, three different narrowband filters that look at the light of oxygen and the light of hydrogen and the light of sulfur. Now, if we were to color these according to where these filters fall on the electromagnetic spectrum, we would get something that looks like this, because oxygen emits a sort of cyan and bluish light. Hydrogen and sulfur are both red. And so this image would have a strong red cast to it if you were to color it according to where these filters lie on the spectrum. So this is where we sort of transition into a representative color philosophy in how we apply color to the data. And so we shift oxygen into full-on blue, and we take hydrogen, which is normally red, and assign it to green, and then sulfur stays red. And so now we have a full three-color image that, I would argue that it's definitely more aesthetically pleasing than the red version, but also I feel allows a little more exploration of the science behind what's happening in this image. The Pillars of Creation are these dense clouds of gas and dust that are being eroded by nearby bright young stars that have these strong stellar winds. And in the three-color, like natural color version, I feel like that process sort of shows itself in the streams that you can see coming off of the large cloud. And again, going back to what I was saying about photography and how we take a photographic approach to this, think of this as like a raw file, right? You get all of the information that you can possibly get from the telescope. You've combined it into a color image, and now this is like your raw file, and you need to do more. You don't want to put an image out that looks like this. At the very least, it needs to be cropped because we can see the edges of the detector here, and we can see some of the sort of ratty information where the cosmic rays haven't been cleaned up. But in addition to that, we'll do some color and tonality adjustments as well. So now I'm kind of stepping through how these would be processed. Some are localized, like that last step there was just applied to the pillars itself. These overall changes, and then cropping and composition. Now, NGC 2020, I wanted to give you some background, some context on that image. So NGC 2020, again, this was our 30th anniversary celebration image for Hubble. We're looking at, the background here is an all-sky view of the Milky Way, and then there's a pullout to 30 Doradus, or the Large Magellanic Cloud, I'm sorry, which contains 30 Doradus. And this is the region where NGC 2020 is located, here. And we designed an observation program for NGC 2020 that was fairly robust. We ran into some problems with it. We lost a few observations, and we had a big hole in the middle for a while. But ultimately, we were able to fill that in. We had 36 orbits on Hubble, and so it's actually a 4x3 mosaic. Hubble actually has a very small field of view on the sky, and so if you want to see something as large as NGC 2020, you have to take multiple exposures and shift the telescope and create a mosaic to see something that's larger than Hubble can see. This is made up of 2 broadband and 2 narrowband filters. And as I said, we have the problem with guide stars that caused us to have to go back and reobserve, and that's why there's the rotated fields of view for some of these observations. But of course, as the data were coming down and we could see what was there, we knew this was going to be another one of Hubble's iconic images, even before we had all the data. Here was our sort of working version of the image before we were able to make those makeup observations to fill in the gaps. It was unfortunate that we had a hole right in the middle, but again, we were able to fill that in. Here I'm just showing some of our test versions of the image, playing around with how we assigned colors. I obviously didn't want to use this one because it turned out very sickly looking, very green. And then this was the working final version before we filled in the data set. Here's an example of the raw image of NGC. This is actually 2014, the Wolf-Rayet star down to the bottom left. And then stepping through each filter, this is the F814W, so this is the red light. The 657N, this is the narrowband filter that looks at hydrogen. And this is the narrowband filter that looks at oxygen. And then we had a blue broadband filter. And the reason we chose the 2 broadband filters was to be able to get really accurate star colors. Because if you work solely in narrowband, sometimes your stars will have a sort of strange look to them. They may have some kind of color cast. But taking red and blue filters and overlaying those stars onto narrowband can give you, much more natural looking stars. And here was sort of the first pre-processing step. And after we attained the makeup observations to fill in everything, and then the final version, of course. And this is a very high res image, and I highly recommend going to Hubble site and checking it out, zooming in all the way down to the core where you can see things like this. I was fascinated by the sort of cave that you see on the left side of this. It was really an interesting, another iconic Hubble image. Now, we also did a visualization of this, and we often do these for the anniversary images. We'll build a 3D model of the object that we have observed, and then we'll take a flight through it. And for NGC 2020, we did a combination of a few different techniques, where we have one that we call sort of 2.5D or a 2.5D decoupage, where we break the image down into planes and then separate the planes out in 3 dimensions. And then as you move a camera across the planes, you get the sense of depth that even though it's not a full 3-dimensional model, it feels like it has depth to it. But in contrast to that, the other technique we used was actually full-on 3D modeling of the Wolf-Rayet star. And so this is what that would look like if you were to look at it on its side, according to the model that we used. And of course, we don't make this stuff up. In some cases, we have to take artistic liberties, but we do consult with scientists at Space Telescope to get as accurate as possible a model of the object. So in the case of NGC 2014 here, We don't know exactly what it looks like if you were to look at it from the side, but our best guess is based on our consultation with scientists at Space Telescope and also just sort of observing the image in detail. We came up with this model. Now, I would highly recommend, again, checking out HubbleSite.org for more information. And of course, I can't really show videos over a virtual talk like this, so I highly recommend going and checking out the visualizations of NGC 2020 and AG Carina, both of which we've done extensive visualizations for. We did a really nice visualization earlier this year of Eta Carina, which is an interesting, really bright star in the Milky Way. Has really interesting structure to it. And keep an eye out next month. The 32nd anniversary image will be released. I'm actually putting the finishing touches on the visualization for that one. And that should be really good. As an interesting aside, in addition to creating the imagery and the visualizations, I actually also compose the music that goes into some of our visualizations. And so for AG Carina and NGC 2020, those are two that I've done the music for. And the one that's coming up next month, I have a nice piece of music for that as well. WebbTelescope.org. You can go there to learn all about what's happening with Webb. And then, of course, we expect to get the first real science data from Webb will start coming down in June. And we have a really robust, we call it early release observations, EROs. We have a really robust ERO program for Webb to demonstrate the breadth of science that Webb will produce. And so we'll be releasing those observations sometime early July. So definitely keep an eye out for that. If you're interested in trying your hand at processing Hubble data, the MAST archive, the multi-mission archive at Space Telescope, is available to all. It is a little bit daunting to go in there and try to find something. So I recommend, if you're starting out for the first time, there's actually a sort of subset of the MAST archive, which is called outreach imaging. And so if you go to MAST and look for outreach imaging, you'll see that we've provided highly processed versions of the raw data so that you can essentially download. It's still pretty much the raw data. It's a FITS file, but it's been really cleaned up. We've taken most of the artifacts out of the image, and then you can start with something really clean to compose your own color images from Hubble data. And Hubble also hosts the Digitized Sky Survey, or Space Telescope hosts the Digitized Sky Survey. So you can go in here and find pretty much any region of the sky, optical imagery in red, blue, and infrared wavelengths. And it's a great place to start because the images aren't that large and they're pretty easy to work with. So if you wanted to, say, make an image of the Whirlpool galaxy, you could type Whirlpool in, get the coordinates for it, download a FITS image from DSS, and start working right away with something that's a pretty low barrier to entry, I would say. I also run a blog called Illuminated Universe, illuminateduniverse.org, where we talk about a lot of what I presented here tonight. We also talk about sort of the behind the scenes of how the images are created. We go into detail about our anniversary images and the visualizations that go along with them. And so, as I was saying, next month we have another anniversary coming up, and we'll be putting out an image and a visualization, and there will be a blog post about that as well. And that's it. Thank you for your time, and I'm happy to take any questions.
Thank you, Joseph. I have a question. How do you see the third dimension, or how much can you see about it? I'm thinking, how do you do you get a couple different angles? I guess being so far out, you're not getting like a left eye, right eye view.
Yeah, no, that's not really possible. Again, it's mostly sort of intuition and consultations with scientists who have studied these objects in great detail. I would say for Eta Carina is a good example of how also we did a visualization of the Crab Nebula. In both of these cases, there are ways of taking, I think it was infrared observations from Spitzer that allow you to sort of penetrate through in 3 dimensions. And it's not exactly a full 3-dimensional model, but it gives you more insight into the 3-dimensional structure of these objects. Okay. We don't always have that information, but when we do, we of course make use of it to inform the decisions that we make. And ultimately, it comes down to a balance of aesthetics and astronomy. And so we do have to make some artistic judgments in terms of how we present the three-dimensional structure of these objects.
Gotcha. Also, what was the original expected life of Hubble?
Yeah. So, like most of NASA's missions, it's usually like 5 years with an extension to 10. But all of these missions are usually over-engineered, and the limiting factors could be, consumables like fuel, but those are good for like 50 years.
Wow.
So, Hubble is assuming that the gyros continue to function as well as they have been. Hubble has many years ahead of its.
And that's another question: is Spitzer still operational?
Spitzer is not operational. That was
Okay.
decommissioned, I think, 2 years ago.
And with Spitzer being decommissioned, I mean, is there still a need for Hubble once the Webb telescope gets completely up and running? And is there a benefit to still capturing galaxies in Hubble's field of view versus Webb's infrared field of view?
Oh, absolutely. Yeah. Hubble is the only observatory that looks in high resolution in ultraviolet light right now. Some of its infrared and even some of its optical capabilities are starting just now to be eclipsed by ground-based observatories that have adaptive optics. And so we're getting to the point where you can get nearly Hubble quality imagery from the ground.
Wow.
But Hubble is still a powerhouse observatory, and it will definitely, we will definitely take advantage of being able to observe simultaneously with Hubble and Webb to get a more holistic view of, say, galaxies, for example.
Okay.
Yeah.
What is the altitude of Hubble?
Hubble is actually in a low Earth orbit. I don't know the exact altitude, but it's basically just skimming above the atmosphere. And every once in a while, it has to maneuver because there's enough drag from the atmosphere to start deorbiting it.
Gotcha. How about Webb? Did I hear Webb's 1 million miles out?
Yeah, Webb is
Okay.
at Lagrange point 1, which is 1 million miles out. And that is because it needs to be really, really far away from Earth and the moon and even the sun to minimize the interference, the noise interference in infrared from all those objects.
Do we? You said the Hubble Space Telescope has a resolution of 2,000 by 2,000. If you want to close out your share, we can bring you back up on a screen.
Okay.
You said 2,000 by 2,000, and it's got stacked sensors, which makes it roughly 4,000 by 4,000.
Yeah.
Oh, I'm not sure what's going on here. Let me see if I can fix that.
That's interesting.
Yeah. Make sure you. I think you still have your screen. If you go to the bottom where you can do your screen share and hit that, you should be able to close it.
I think it is closed.
I think I'm still seeing you on your screen though.
Okay.
Let me see if I can. Maybe I'll do that. Oh, let me see if I can kick it out from this way. I think we're good now.
Okay.
Do we know what the resolution is for the Webb telescope?
Yes. So Webb actually has multiple cameras. There's the near cam, which is high resolution, and that is comparable to Hubble. I think it's about 4K by 4K. It's an interesting setup of two detectors that are kind of separated by a large gap, and most observations are going to mosaic across the gap. So you're going to get even higher resolution from Webb in near infrared. But in longer wavelengths, Webb is actually lower resolution than Hubble. And its mid-infrared instrument, MIRI, that's actually like a 1K CCD.
Gotcha. For some reason, I have your desktop back up again.
Yep. Okay. Turn that off.
Yeah. There we go. I think we got you now.
Great.
Photographers have a big problem with sensor dust. Is that a problem out in space?
That's not so much a problem in the vacuum of space. Well, I worked for Chandra for years, and the problem there was actually outgassing of some of the materials that were used to build the telescope. And when you have these sort of volatile materials outgassing, they want to settle on the coldest surfaces possible. And of course, for Chandra, the coldest surface was the focal plane of the instrument. And so Chandra had this, we called it the gunk buildup on the mirror in front of the mirror, in front of the detector, that actually reduced the low energy sensitivity to X-rays over time. But dust is actually not a problem for Hubble.
Oh, good.
Yeah.
Are galaxies so far out that you can just point in one direction, or do you kind of need to do something like a star tracker? Do you need to move with distant galleries?
Yes, so Hubble has, and Webb as well, they have these fine guidance sensors that when we point somewhere, they'll lock on stars that are nearby, and it constantly maintains a view on those stars. And of course, in both cases, the observatories are moving. So yeah, you have to track. And if you don't track, you get horrible artifacts in your images and streaks that run across. It happens with Hubble from time to time.
I have a question from chat. Scott asks, you speak of music and art in relation to your creating of these images. What is your background on that?
So my formal training is in astronomy and astrophysics. I went to Villanova University, graduated in 2001 with a degree in astronomy. And then I started working for Chandra right after that. I have a strong interest in painting and art and music and photography that I've maintained for my whole life. So I feel like, again, it's sort of when I moved into public outreach and making these images from Chandra and from Hubble, it was sort of bringing my interests together to create a job that, and now with the music too, it's a job that hits all my buttons.
That's pretty cool.
Yeah.
Let's see. You said the Hubble. You had a Hubble image take 600 hours. Can you talk about the selection process on going from somebody saying, "Hey, I want to point Hubble in this direction"? How long does it take from approval to actually starting to capture the data?
That's a great question. Yeah. So Hubble has every year there's a call for proposals where scientists from around the world can submit proposals to observe with Hubble. And there's a cutoff date. I think it's sometime in March, maybe April. And the proposals are all collected and they're peer reviewed. And Hubble was actually one of the first NASA observatories to institute a double-blind peer review process. And this was just a few years ago to minimize any kinds of biases that could be present in the review process. Because if, scientists like big name scientists are on a proposal, they're probably going to get the time that they want, which then, of course, is to the detriment of early career scientists. So doing a double-blind review process, nobody knows who's submitting, nobody knows who's reviewing. It's turning out to be a very equitable way of reviewing these proposals. And so that's the process. You submit a proposal, it gets reviewed. If it's approved, sometime in the following year, you will be scheduled. And the schedule is determined based on, where maximizing the efficiency of observing with Hubble. So if you have a time constraint to your observation, you can put that in your proposal. And of course, the mission planners will try to honor that because otherwise you wouldn't be able to get the data that you need. But yeah, so that's how that works. There's the proposal process, the review, and assuming that your proposal is approved, you'll get time on Hubble in the next observing cycle.
Gotcha. Is there a kind of like a PR firm that checks these images before they go out to the public? Like, what if you find little green men somewhere? Is there somebody what would happen if you saw something like that and it may cause a stir? Is there kind of like a review before those images go out to us?
Oh yeah. There's a lot of steps in the review process. What I usually end up doing is for most of our press releases, it's to promote some science result from Hubble. And I actually work closely with the scientists who have provided the data to make sure that the image is, what they would expect to see. Most of the times it's something that they didn't expect to see because it's much better than what they could produce themselves. And they're extremely excited to see their data, presented in such, colorful, dramatic way. And then from there, it's reviewed by NASA headquarters. And so there's multiple levels of review before anything goes out.
Interesting. Put a last call out for questions. Joseph, are you going to still continue to work on Webb images as they come in?
Oh, yeah, absolutely. In fact, that's why I was hired at Space Telescope 5 years ago. When I was hired then, Webb was supposed to launch in 2018. So they were, they're undergoing like a hiring bump in preparation for Webb. And then there were a bunch of delays, but Webb's up now, and I will be working on the Webb imagery for the EROs, and I can't wait for that. Really looking forward to it.
That's great. Can we hear your music on the illuminateduniverse.org page?
I don't think I have music on there. There's a few of the blog posts talk about how the visualizations were made, and I think for one of them, I do go into a little bit of detail about how I composed the piece for that. Mm-hmm. And I'll be doing the same for the one that's coming out next month. I really need to get like a SoundCloud or something for the music I've been producing, because otherwise it's really not available anywhere. It's just on the Hubble site for now.
What kind of musical instruments do you play? What's your favorite, and why is it the theremin?
I love that. Yeah. So I'm a guitarist. I play in a band, riding shotgun, and I've been with these guys for almost 20 years now. Unfortunately, when I moved here, I left my band. We were a trio, guitar, bass, and drums, and the bass player and the drummer are still in Boston, where I lived before I moved to Baltimore. So I'm mainly a guitarist, but I also have recently really gotten into synthesis. And the more recent music I've been working on has a lot of synthesizer work in it. In fact, I've kind of let go of guitar for the Hubble stuff. It just doesn't. I feel like it doesn't quite lend itself to space. I have a lot of effects pedals that I really like, and some of those I'll put a bunch of those on and create like sort of space soundscapes with my guitar. But lately, it's been more synthesizers than guitar.
No theremins.
Yeah, theremins.
Well, the synthesizer is kind of more the big boy theremin, right?
Yeah. In fact, one of the synths I have just recently got is a Moog, so it's a direct descendant of the theremin.
Oh, very cool.
Yeah.
Well, Joseph, I think that's it. I don't have any more questions. I really want to thank you for joining us. I mean, this is a mind blowing talk, and yeah, just being able to kind of live vicariously through you when you showed us how the images come down and how you edit them together and put them together for public consumption. That's just absolutely fascinating.
Well, thank you. Yeah, I'm really happy to be doing it.
Yeah. Well, thank you again, Joseph. Everybody everybody listening here, remember we have a field trip to the cherry blossoms down in Washington, D.C. this Saturday, and make sure to join us next week for Quinn Jacobson's talk on alternative process photography. And with that, I'm going to say good night. Good night, everybody.
Good night. Thank you.